In this video, we will be going over the Gram Schmidt process to make an orthogonal basis that will span the same space as these two other vectors. Notice these vectors are not orthogonal. They are not perpendicular. Their dot product is 22. It is not 0. If the dot product is 0, it's an indication that your vectors are perpendicular. These vectors are not perpendicular. But they are independent of each other. They're not on the same span, the same line. And so the Gram Schmidt process will help us find another pair of vectors that span the same space but are perpendicular to each other. Why we're focusing on perpendicular is because the shortest distance to any path or surface would be the perpendicular distance. So eventually we will use these orthogonal bases to help us find the best fitting approximations of points to other surfaces. Alright, so here is what our process will consist of. Again, we're trying to find another pair of vectors that will span the same space as these two vectors, but will be perpendicular to each other. Well, why don't we just let the first vector be one of our vectors? So I'm going to let the first vector in the new set be vector A. There, done. I've already found one of my vectors. Now I need to find a vector that will be perpendicular to A, but will also be in the same plane as AB formed. And here is what we do. We actually take B, the other vector, and we subtract the projection of B onto A. And how you can compute the projection of B onto A is by taking the dot product of the two vectors, B dot A, and divide that by the dot product of A, and that gives you a scalar, or a real number, and you multiply the vector A by that, and that will give you a vector that's projected onto A, but when you take B minus this new vector, it will give you a vector that is perpendicular to A, but still in the same plane that AB formed. So following through with that, this is vector B, and remember B dot A was 22, and A dotted with itself is 18. So notice 1 squared plus 1 squared plus 4 squared is 18. That's what A dot A is. And so then that gives us this new scalar, 22 over 18. I'm going to multiply vector A by that. And now I will clean it up a little bit. So the vector 283, I'm going to subtract 11/9 times vector A. I just divided 22 and 18 by 2. And if I distribute the 11/9 through vector A, this is the vector I get. And if I carefully do that fraction arithmetic, I get a new vector V2 with first component 7/9, second component 61/9, and third component -17/9. So again, here were my two original vectors, 114, 283. And I have found this new vector 7/9, 61/9, -17/9. You can see here that A and this new vector are perpendicular to each other. They are forming a 90-degree angle, and A and B did not form a 90-degree angle. You also can tell that those two vectors fall in the same plane. So this is the plane that contains all three of them, and all three of them fall in the same plane. So vector A and this new vector V2, they span the same space as A and B, but they are perpendicular to each other. Now this process stays the same process whether you're in R2 or R3 or in a higher dimension, and whether you have more vectors. Now in this next example, we have three vectors in R4. They are fourth dimensional vectors, and the three vectors are independent of each other. You could check that by finding like RREFing and, you know, seeing that they're independent of each other. Also, they are not perpendicular to each other because their dot products are not 0. A dotted with B is -36. A dotted with C is 6. B dotted with C is 12. They're not 0, therefore they're not perpendicular. So they will span some space in 4 dimensions, and we want to find a set of vectors that will span that same space, but the new vectors we want to be perpendicular to each other. So like with our other example, let's just make things easy on ourselves and let's pick the first vector to be one of our vectors. I mean, we want it to span the same space, so it would be okay to have one of the vectors be one of our original set. So I'm going to let V1 be A. Then V2, I will compute by taking B, the second vector, and I will subtract the projection of B onto A. And so this is vector B, 6, -8, -2, -4, and B dotted with A was -36. A dotted with itself, which is actually the square of the length of A. Again, that might be something you've learned about vectors, but a vector dotted with itself gives you the length squared. So it's like you found the length but then didn't take the square root. So A dotted with itself is 12, and then I want to multiply vector A by that scalar. -36 divided by 12 is -3, but I'm subtracting, so that turns this into an addition. And if I carefully do that arithmetic, I get my second vector is 3, 1, 1, -1. So I now have 2 vectors in my set. I need to find a third vector to span the same set that A, B, and C span. So I'm going to do a similar process, but this time I need vector 3 to not just be perpendicular to A, I need it also perpendicular to this new vector that's in my set. So I take C and I subtract the projection of C onto A, and I subtract the projection of C onto this new vector that we just found. So C dotted with A was 6, and C dotted with the new vector that we just found is 30. And A dotted with itself is still 12, and my new vector dotted with itself is also 12, because we've got this combinations of 1s and 3s. Okay, so here's vector C. This was vector C. Again, it was in our original set. And I am then subtracting. C dotted with A was 6. A dotted with itself is 12. This is vector A. Then I'm subtracting C dotted with the new vector V2. And then V2 dotted with itself is also 12. And then this is vector V2. Notice 3, 1, 1, -1. And 6 divided by 12 is a half, and 30 divided by 12 is 5 halves. And carefully doing this fraction arithmetic, I get, again, vector C. This is the projection of C onto A. This is the projection of C onto that new vector. And I subtract and clean it up. And my third vector then is -1, -1, 3, -1. So notice, like 6 plus a half would be 6 1/2. I'm subtracting a negative, but then I'm subtracting 7 1/2, because 15 halves is 7 1/2. So 6 1/2 minus 7 1/2 is where I got that -1. And 3 minus 1 1/2 is 1 1/2, but then I'm subtracting 5 halves, or 2 1/2. So 1 1/2 minus 2 1/2 is another -1. And then 6 minus a half is 5 1/2. And then I'm subtracting 2 1/2. So 5 1/2 minus 2 1/2 is 3. And then again, if I carefully did the last thing in arithmetic, I'd get -1. If you check the dot products, you will see that V1 dotted with V2 is 0, and V2 dotted with V3 is 0, and V1 dotted with V3 is 0, so all three of them are orthogonal. So these three vectors, V1, V2, and V3, will span the same three-dimensional space in R4 that those original vectors spanned, but these three vectors are orthogonal. If you wanted to go one step further and make these vectors unit vectors so that they just have length 1, because a lot of times some of what you're working with becomes cleaner if you know your vectors have length 1, then you could form the orthonormal set. Orthonormal meaning you've created vectors that are length 1, and you just take each vector and divide each component by its length. All three of these vectors happen to have length 12, so that's why we're dividing all the components by 12. Going back to the original premise here of what we are doing, that again, you're creating perpendicular vectors by subtracting the projection of one vector onto another. And a little review about some other things related to dot products. Cosine of an angle in between two vectors would be the adjacent side over the hypotenuse, and so in this case the adjacent side is a length on vector A, and the length of B is the hypotenuse. And also it can be shown that the angle between two vectors is equal to the dot product divided by the lengths of each vector. So if I replace cosine of theta with that expression and set it equal to what we know cosine of theta does equal from right triangle trig, we get this cleaning up to be what we're using here. That we have the dot product of the vectors, and then we have length A, and when we multiply by the unit vector of A, that means we're multiplying by A divided by its length. And as I said earlier, the square of the length of any vector is the same as its dot product with itself.